Let's talk about unit testing. So we introduced unit testing last time, talked about what it is, how to set up a test class, how to write tests, how to write test cases, and what to think about when we're writing test cases. So let's continue that conversation, and specifically, we're going to talk about testing strings and doubles today. So let's do it, and let's start with a demo. So we talked about this stuff last time, but we didn't actually, now I got all this open. But we didn't actually see it in action, so let's see it in action. We had the add 5 method. Once I get all these done. We had this add 5 method, this beautiful method that adds 5. And we had our tests for this method. We had test add 5 for our common cases, our negatives, our edge case. And I'm going to throw 2 more at you here. I'm going to test the edge case a few more times, and I'll talk about those once we run this thing. So once we have a test class, there's no main method in a test class. So to run this, we run it the same way we do a class with a main method. There's actually no difference. IntelliJ will see that this is a JUnit test class. And in fact, we have all these buttons here. It's recognizing it and seeing it as a test class. So to run this, we have a lot of buttons here. We want to make sure we hit the right one. You want to hit the one associated with the class. We want to run the entire test class. If you hit one of these buttons next to a method, it will only run that one test. So you want to make sure you're running your entire test class, all the tests in that class. So make sure you click next to the class, or what I like to do is right-click on the class in the sidebar and then run it that way. That way I'm making sure that I don't accidentally click the wrong thing, because I can't make the mistake if I'm right-clicking the class in the sidebar. And when you run your test, you're going to get output like this. It's going to give you feedback about each one of your test methods and how they performed. Here I got green check marks all the way down. This is what you want to see. This means the code passed all of the tests. Everything passed. And when everything passes, there's really not much to see down here. You get green check marks, your test passed. What more do you want? You don't need any more information after that. So let's do something more interesting and watch a test fail. I'm going to take my bad on 0. I'm just going to rename this add 5, so this is the one being tested. And I want to test my method that's wrong when the input is 0 and rerun this test. Now, and I want to make sure I talk about this. I've remembered in both lectures. Now that I ran the add test method, now I can use this green go button up in the top bar of IntelliJ. What this button does is runs the last thing that you ran. So when you first open IntelliJ for a new project, if you haven't ran anything, this button will be grayed out. You won't be able to use it. But once you run something, it will run the last thing you ran, or you can use this drop down and get a short history of the things that you ran recently and choose which one you want to run. But this will run the last thing that you ran. So if you cloned the repo in lab last week, you ran hello world, and then you go to run this test. You want to play around with the add tests thing. You want to see what's going on with that. And to run it, you just click this button. Well, guess what? It's going to run hello world again. This won't run the code that you're currently editing. It's going to run the last thing that you ran. So just be aware of that you could be running the wrong thing. You could be running something you don't want to be running. Okay. So now we reran this, and we have failing tests. This is what we're going to see when a test fails, is this yellow X, this circle with an X in it. This means at least one of the test cases in that test failed. That the assertion did fail. It ran the code and said, this code is no good. And we get feedback like this. So we ran this test add 5 edge case. We got an assertion error, which means that assert true, which is asserting that this Boolean expression resolves to true, which is only going to happen if adder.add5 of 0 resolves to 5, and then equal 5. So this resolved to false. So we got an assertion error, and it's going to tell us what line number failed. So if I click this, it'll take me exactly to the line where the assertion error occurred. So I can tell which specific test case. There's only one in this method anyway. But which test case was the one that failed? And if there are multiple test cases, and if I did the bad on negatives one, and it'll say this test case failed, and then the program ends. The test ends right there. So if this one fails, all of these test cases never get executed. These ones never get checked at all because the test ended as soon as one of them failed. So just keep that in mind. If you fail like that test case, it doesn't mean you got the other 4 correct, but it means that this one failed and then ended the test. So I get this feedback. It tells me which line failed, but that doesn't tell me that much. Like, I don't get much information. And assert true can't give you much information. Assert true is checking if a Boolean expression resolved to true. So if it resolves to true, the test case passes. But if it fails, if the test case fails, the only possible thing that could have happened is that Boolean expression resolved to false. That's it. So there's nothing to tell you. The library can't help you out here. All it can say is, hey, that test case failed, right? What else do you want it to do? It was supposed to be true. It ended up being false. So I'm going to go to the next thing. And I know I skipped a few slides at the end of last time. I'm going to talk about them in IntelliJ. I'm not going to go back to those slides. I'm going to say the same thing that I want to say in IntelliJ. So we can use something else. We can use something a little fancier, I suppose, called assert equals. Instead of using assert true, we have another method called assert equals that's part of the JUnit library. So I have to import it just like I did assert true. I'm going to do a static import for assert equals. Or actually, I could do this if I want to import all of these methods, all of the assert methods. I can replace it with a star. But you have to make sure you're importing each one way or another. And assert equals is kind of like assert true in that if the test case is defining a test case, and if that test case fails, then it's going to fail the test. But instead of asserting if a Boolean expression resolves to true, it's going to take 2 arguments and assert that they're equal. You could probably have guessed that. It's going to take 2 arguments. Here, 5 in result. I'm expecting this value to be 5, and then give it what I actually got, and it's going to check if those 2 values are equal. So one big advantage of this right now, we're going to see a few advantages to this, but one big advantage of using assert equals is if the 2 values are not equal, I actually get some meaningful feedback here. I don't just get, hey, your test case failed. The library is going to know that I expected these 2 values to be equal, and it's going to say, look, you told me this was supposed to be 5, but this is what I actually got, is actually 0. So instead of saying, hey, your test case failed, which only tells us that result was not exactly 5, now we actually get the information of what the hell result actually was, which is going to speed up our debug process. Any more extra information that we can get is really going to help us eradicate the bug that we've identified with this test case. And we can take this a step further with something called hint text. So any of these asserts, we've only seen 2, but assert equals and assert true, or any other asserts that you want to use or that you'll see throughout the semester, you can add another argument. You can add a first argument. You add it, but it comes before the other ones as a string. So now my first argument is a string, and then I have my expected value and my actual value. This string is going to be printed to the screen if the test case fails. So in this, using these hint strings, this hint text, you can give yourself more information than what the library is going to do. The library will give you expected and actual, but maybe you also want to know what the input was. Here on this one, it's straightforward enough. If the expected was 5, I know my input was 0, and I can go to the line of that test case and deduce it. But you can't always do that. You can't always figure out exactly what the input was. You might have multiple inputs with the same expected outputs, or your test cases might get fairly complex. You want that information readily available. If you print out the input or any other information that you want, if the test case fails, you can print out more information to help your debug process. So here, when this test case fails, I get my hint text printed to the screen. I can see result was 0 on input 5 or on input 0. I expected 5. and the library, since I'm using assert equals, is still going to give its hint text of what was expected versus what I actually got. So those two things, hint text and assert equals, can really help your test cases. When you write a test case and that test case fails on your code when you run it, give yourself hints to figure out where that bug is, what that bug is actually coming from. Right. And I kind of mentioned what, talked about it for a bit, what the Autolab feedback looks like in IntelliJ. Oh my goodness. I get IntelliJ and Autolab mixed up all the time. What the feedback looks like in Autolab. Right. But I want to show some actual feedback. I checked this morning and like 40 students out of both sections have even submitted task 1 yet. So I know most of you haven't seen any Autolab feedback yet. By the way, get on that. Like y'all can, after today's content, you have everything you need for programming task 1. There's nothing more for me to show you. I can give you tips and tricks on Friday's recursion, actually. I won't even have time for tips and tricks, except right now, I guess. But there's no more content for me to tell you after today. You'll have everything you need to prepare yourselves for programming task 1. Yeah, got everything you need. Nothing stopping you. So I want to show you what the feedback is going to look like when you start submitting. So the first thing here, aside from some overhead here, is going to be the output of unzipping your zip file. I have this here to make sure that you can verify that the zip file was extracted properly, that you have all the files that you expect, that the directory structure is what you expect. Make sure nothing went wrong with the zip file itself. We used to have a lot of issues with that. I started printing this out, and now students can find the issue and fix their zip files. So just to make sure that you have all the stuff that you expect in that zip file. And then the first bit of feedback you're going to see is testing your tests on a correct solution. Should we make a new class for each test case per problem, or just bunch all the tests and problems under one class, respectively? Under one class. So in the homework, it says write a test class named test problem set. So all of your tests have to be there because that's what Autolab's looking for. Autolab's looking for one class called test problem set. So if you create a second one that's like test problem set average, Autolab won't be able to find that because it's not expecting that. But you are strongly encouraged to write your test cases in multiple test methods within that class. So at the very least, I would write 3 test methods inside that class, 1 to test average, 1 to test sum of digits, 1 to test largest key. Is that what it's called? Best key. So at least separate the 3 methods into 3 tests at a minimum. But even that's optional. You can jam it all in one test if you want. But if I have to stare at that in office hours trying to figure out what went wrong, I'm going to be a little, not upset, but it's going to take me longer to answer your question, I'll say, and the TAs as well. It's going to take us longer if your code's a complete mess. So at least do some basic level organization of your code. And also, I encourage you to separate them into separate tests. So I have one test class named test problem set, which we can verify we have right here. And that test class has these test methods. So you'll see feedback for each one of the methods in your test class that you submitted, and you'll get feedback on those individually. So I want to see, will Autolab fail my tests, but JUnit pass them? Wait, what? Will Autolab fail my tests, but JUnit pass them? Maybe. It might. So a correct solution, I'll expand on that, but it's what I'm about to say here. If not, ask again, and I'll let you know. So the very first thing, what's going to happen, I'm going to take your test problem set class, and then I'm going to take my solution code. So I'm going to take your code that you submitted, take out your problem set.java, and replace it with my problem set.java with a correct implementation of all the methods, and run your test suite, your test class against my solution. Now, your tests, if your tests are testing what they're supposed to be testing, should pass my correct solution. So it's possible for Autolab to say you failed on a correct solution. In that case, this is all the feedback you're going to see. The feedback will stop right here, and you won't see any of this next stuff because you didn't get past phase 1 of passing a correct solution. And I'll tell you, if you do fail a correct solution, it'll tell you which one of your tests failed it, so you can identify which one is the problem. This is my way of encouraging you to actually split these into multiple tests. If you have one test called the test, and it says failed correct solution, you have no idea where to start looking. You have to look at your entire testing, everything. But if it's broken down like this, you actually separate them, you'll be able to identify which one is causing the problem. It'll speed up your process a lot. So if any of them are failing a correct solution, that means what I always recommend is go back to the homework handout, reread everything, make sure you have everything the way it's supposed to be, because somehow you have a test, at least one test case, where your expected output that you're testing for isn't actually what it's supposed to be returning. So there are ways that can happen. There are a few assignments throughout the course where that is more common than not, but more common than others, I should say. But that means something went wrong. You did something just wrong, I guess. Or if there's an error, you'll get this won't even show up because Autolab can't even run your test. And it'll say, hey, double check the document. You got something way wrong. Usually a misnamed method or a misnamed class or the wrong types of some variables, some parameters or return types, something like that, where you're just not in line with what the homework handout asked for. So if you're correct on a correct solution, then you'll move on to the incorrect solutions, and you'll see this feedback. For this, and this is probably the biggest source of confusion when we first start doing this, I've reworded these things so many times. I try to make it simpler, but it's still, it's just confusing. It's just something we'll all have to get used to. Or if you have suggestions on how to word this better, I've taken suggestions and updated how I write these things multiple times from students and TAs. If we can do even better, let me know. But I'm going to take your test, I'm going to remove my problemset.java and replace it with an incorrect solution, code that's intentionally wrong. This is just like my add 5 no negatives. I'll replace it with this code that's intentionally incorrect. And I'll put that code in place of my correct solution. So I'll have an incorrect solution. I'll give you the name of it. This is supposed to be some cryptic hint, just a vague name of what it is, to give you somewhat of an idea of what the incorrect solution is. At least for problem set 1, it'll tell you which method it has incorrect, is a pretty good hint. But average bad on large list, I mentioned this last time. I don't know, since it's homework 1, I'll spoil a few of these. I won't always spoil the incorrect solutions. But average bad on large list would mean that my average method isn't getting the right average when the list is sufficiently large, which I think is size 3 or 4. It's not super large. But what this is doing is making sure you have at least one test case that has an array list of like size 5. If you have an array list of size 5, you're going to get rid of this one, no problem. But you should have a test case that identifies that bug. How are we doing on large lists? Is the solution good on large lists? And then similarly, your feedback on all your tests. Most of these tests did not reject the solution. That means this test passed when running against this incorrect solution, which is okay as long as at least one of the tests, this test average, which as the name implies is my only test that's actually testing the average method. So if there's a bug in the average method, this is the only one that had a chance of failing it. You'll get successfully rejected the incorrect solution. That means this test here had at least one test case where this incorrect solution did not return the right output. And we demand perfection in our unit testing, but when we're testing incorrect solutions, that perfection works in our favor, is that you only have to have one test case in one of these tests failing that incorrect solution for your test to say that is an incorrect solution, and that's what you want. Your test correctly rejected that solution because you had at least one test case in one test that rejected that solution. The solution isn't perfect, therefore it's wrong. Yeah.
Yeah. Can our code/test timeout on AutoLab?
Yes. Yeah, but that's pretty rare unless there's something really, really wacky going on. Usually if you're seeing a timeout in AutoLab, it means you went infinite. And whatever the timeout was, it wouldn't matter. For what it's worth, it's set for 3 minutes. which is a lot of time. So for each incorrect solution, average bad on large list, average bad on singleton. I always get this question. I mentioned it last lecture, so let's talk about it right now. That a lot of you haven't heard the word singleton before. I kind of took for granted when I wrote this. But singleton is a data structure with only one element in it. So average bad on singleton, if you give it an array list with just one value, and the average should just be that value, right? This incorrect solution will not return the right average on that input, which is a good edge case. How are we doing when we're supposed to average a bunch of values together? That's what the method is supposed to do, but we only have one value. It wouldn't be too hard to write a bug accidentally, hopefully, that is wrong on singletons. Average off by 1. This is one of my free ones. I usually have at least one incorrect solution that's just the free one, like, are you testing anything? Average off by 1. The average is always going to be off by 1. So it always returns the wrong thing on every single input. You should always get that one out of there. Digits, no negatives. Hopefully I talked about it enough last time. I hammered you should be thinking about negative numbers. If you're not thinking about negative numbers, you're going to be passing this incorrect solution. You're going to be not rejecting this incorrect solution. Digits off on 0. Hopefully it was pretty clear last time too that you should be testing your edge cases. 0 is an edge case. If your sum of digits method doesn't handle the input 0, I know you didn't even pay attention in last lecture. You're not gonna get through this incorrect solution. Digits, only 3 digits. So taking the sum of digits, making sure you have something that has at least 4 digits in it. Key bad on empty. It's explicit in the homework handout what you should do on an empty hash map. Did you test for that? Key bad on multiples. So do I have multiple best keys, and how should we handle that? And key bad when best is negative. These are all the incorrect solutions for this homework. So you need, for each one of these incorrect solutions, I'm going to take your test, put in my incorrect solution, run your test against my incorrect solution. Swap it out for the next incorrect solution, run your test again. And swap it out each one. For each incorrect solution, you need at least one test case that's going to identify that as an incorrect solution. So your test should fail that code and say that's an incorrect solution. In theory, at least, the idea is that you'll sit down and write a good test suite. Think about all of your different test cases, your edge cases, come up with some large test cases, some small test cases, get a nice variety of test cases, throw them all into Autolab, and Autolab will be like, damn, that's a good test suite. You're good on all the incorrect solutions. I see far too many students, and a lot of you will do this. I have no way of stopping you, but you'll write almost no tests, submit, get all my test names, and try to reverse engineer every single one of them. I don't recommend that at all, but I know a lot of you will do it, and you will waste a lot of your time doing that. It'll be a lot faster if you just sit down and write a good test suite. But I can't stop you from wasting your time. I've tried before. I try less now because it's a losing battle. But the only solution I have to that is removing the hints. And I don't really want to do that. Someday, but not this semester. I ain't going to do that. So if you do get all the incorrect solutions rejected, if every single one of them is rejected, and only then will you see the third stage of the output. This is taking my tests. I have my test suite and then your code. So my test problem set.java and your problem set.java. And I run my tests on your code. And I give you the output of what happened when I ran my tests on your code. And of course, have to pass all my tests. This is usually the easiest part of the assignment, at least in terms of surprises in Autolab. If you have a test suite that Autolab's happy with, you thought of all your test cases, you got rid of all the incorrect solutions, you're passing a correct solution, and you ran your test suite in IntelliJ and your code is passing your own tests, then usually this part's free. If you have a good test suite and you're passing your test suite, this will just, the first time you see this output, it'll say pass, 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 pass. Now, in later assignments, sometimes when I start backing off in the testing, you will have a lot of surprises here. If you're the type of person who reverse engineered my incorrect solutions and have the absolute bare minimum testing, which a lot of you do, Then there will be surprises here, and you'll have to do a lot of work here. But especially for problem set 1, I require the testing to be pretty comprehensive. You're not going to have surprises here. Okay, any questions on Autolab output? Can we submit the test code without writing the actual methods and still receive this response? Yes. And especially for problem set 1, for later problem sets where you have to write. Why am I blanking on how to word this? But for problem set 1, I gave you the method headers, and then I put to-dos in there. For later ones where it's like write a class that has these methods, you do have to at least write the class and then put the methods in with to-dos or just empty methods or just return 0 or something like that. They do have to exist just so the grading code can compile and run against your code, but you don't have to actually write the methods. So especially for problem set 1, you can start with your tests, and you're encouraged to start with your tests, write your tests, submit to Autolab, get your testing feedback, and then once you're happy with your tests, then write your code. There's something called test-driven development, and if you have a good, solid test suite or test class, before you write your code, it makes it a lot easier to write your code because you write some code, you think it's right. How do you know it's right? You run your tests. If your tests pass, then you're pretty confident that it's going to be right. My goodness, 2:27 already. All right, we gotta keep going. So I have this beautiful method, similar to our add 5 method. It's not too complicated. It's going to take 2 strings. It's going to concatenate them together with a space in between. I have this test case for the class. It's going to take 2 strings, hello, goodbye. It's going to call combined strings and assert that the output is hello space goodbye, which we expect it to be. That's what it should be. We just saw the code. Pretty certain that's what it's going to be. And I am going to use this button intentionally. I only want to run this one test, so I'm going to use this one. And the test fails. Why does that test fail? Is a question we'll answer in the slides. I got another surprise for you. It's not a surprise because I'm introducing it like that, but times 3, very simple method, takes a double, multiplies it by 3, and returns the response, returns the result. I have this test. Oh, I added this in. If you're wondering how to populate an array list in one line, arrays.asList is the answer. I stuffed this code. Somebody asked last lecture, I stuffed it in this method, but if you're wondering how to do that, let me just comment this out. That's how you do it. Arrays.asList, but don't forget to import your arrays class. I'm calling times 3 on 0.1. We expect the result to be 0.3. I'm going to assert that the result is 0.3, and you guessed it, it's going to fail. And I'm giving you a little hint here. I'm printing out what y is, and it's 0.3 almost. It's got this trailing 4 way out here. So we compared 2 strings, didn't get what we expected. We compared 2 doubles, we didn't get what we expected. So let's talk about that, why that is the case. So testing strings. Why did this test case fail? Why does this fail? It seems so straightforward. We're just concatenating and then making sure we got the right value. And the short answer is because we're using equal equal to compare 2 strings. Never use equal equal to compare 2 strings. And spoilers, never use equal equal to compare 2 doubles either. So equal equal to compare 2 strings is not checking what we want it to check. So strings, we do treat them as they're on the stack in our memory diagrams, but this is the one case where we do actually have to care that string starts with a capital S, it's a non-primitive value, that it is actually on the heap. And when you compare 2 values that are stored on the heap, or 2 variables that store references to objects on the heap with equal equal, what it's going to do is check if those variables refer to the same object on the heap, which isn't always going to be the case with strings. It sometimes will be. If I set this example up to be a little simpler, sometimes it will say, yeah, that's good. But the way it's set up, It's not going to be. It'll sometimes work, it sometimes won't. Don't rely on equal equal to compare your strings, because you're going to have really strange, hard to find bugs if you're relying on that, because it's not always, bless you, because they're not always going to be referring to the same string. They sometimes will be, because strings are weird, that sometimes references will share the same object, even though they're two different strings, kind of, but not really. They're weird. So instead, we're going to use the equals method. We're going to take a string, the string that we get here, and dot equals whatever string we expect it to be. Equals is going to compare the strings by value, not by reference. And in fact, this is the way we want to compare any two values that are not primitives and not doubles. There's very few things we can actually use equal equal to compare for equality, which is our ints. Goodness, is that the end of the list? Oh, and booleans. If you want to check two booleans, I guess. That's it. Like, there are other types that we don't use in the course, like shorts and longs. Those we could use equal equal to on as well. But for this course, yeah, booleans and ints. Those are the only two, aren't they? Chars, we don't really use chars though. It's too much. But this test passes and we're good. This is going to check the values. So using dot equals on our strings is what we want to do. And I'll one up that a little bit and talk about assert equals. We used assert equals in the last example in IntelliJ. Assert equals is going to do the same thing as equals. Assert equals, if you give it two strings, this library is smart enough to understand, hey, I got two strings that I have to compare. I'm going to use equals, the method, not equal equal, the equality operator. It's going to use the equals method, and we'll get that bonus advantage of more feedback. If this string isn't the string we expected, we're going to get that expected and actual. We're going to get more feedback on that. And I always do this backwards. It should be hello, goodbye, and then the method call. It should be what you expect first, and then what you actually got second. I don't know why, but I always forget that, and I always do it backwards. The only difference here is that when the values are printed to the screen, it'll say expected this, but that'll actually be what I got from the method, and then actual is this, which is actually my expected value. So I'll have those printed backwards, which doesn't really matter, but I really should update the code in the slides. Okay, so whenever we compare strings, we're using the equals method or assert equals. Never use equal equal to compare strings. So let's revisit some code that we saw last week. We had this letter method. I cleaned it up a little bit. I got rid of that extra variable that I used just to talk about variables inside code blocks. And adding this method, this plus minus, which is the one we want to look at today, I'm going to say anything 7, 8, or 9 in the ones digit, we're going to give a plus to. Anything 3 to 6 is going to be no modifier, and then 0 to 2, we're going to give a minus modifier to. So we have pluses and minuses on our grades. And we have this beautiful main method with 3 test cases that we're going to verify manually. But we're beyond main methods, so let's rewrite these test cases in a test class. So let's rewrite these. So we're going to call our method, get the modifier, either plus, minus, or empty string, and then have a test case to make sure that it is what we expect it to be. And of course, I have my arguments backwards again. I'm going to add my hint text, so I get a little more information out of the library, out of this assert if it fails. And I'm going to check what I got. Is it what I expect? Is what I got what I expect? Is what I got what I expect? So with 95, I expect no modifier. 78, I expect a plus. And 51, I expect a minus. But do I really? We can argue, I would argue anyway, that that's a bug in the code, that 51 should not be a minus, because at that point it's an F. An F minus is just an extra insult. And then 49 would be an F plus. You would get a better grade for going down. We do have some bugs in this code, which is why it's written like this. If we get to it later in the semester, I do have content for that. I don't know if it's going to fit in this the structure this semester. But we would go through and fix all the bugs with this. Okay, so we're happy. We passed those 4 tests. And of course, we would want way more tests if this were an assignment for a full test suite. And if we do get to it later in the semester, we'll do this. I want to check every boundary of every letter grade, the grade right before that boundary and right after the boundary. I would check all of those. I would check our edge cases and negative numbers, values over 100. There are a lot of things I'd want to test with this method, these methods. But let's at least get one edge case. Let's check 100. And our test fails. So on input 100, the way we're checking for our plus or minus, our ones digit's going to be 0, which is going to hit our else, and 100 is going to get an A minus. This is an upset student. I'm going to get emails and a student knocking on my office door. There's going to be problems, as there should be. To get 100 in a class and then get an A minus instead of the A plus you deserve, bad news. But we passed 3 out of the 4 tests. Like, for our code, that's a 75%. We had 6 more test cases here that all passed. We got a 90%. We're feeling good, right? No, we demand perfection in our test cases. We want our methods to be right on every input. So we're demanding perfection, and the student that just got that A minus certainly demands perfection as well. They got 100 all semester. We want to make sure we fix this bug. So the point of this, the idea, is we want to think of test cases that are going to expose specific bugs. That's our edge cases. Last time we saw our edge cases is 0 for the input, and then I gave examples of empty string, empty array list, empty hash map. Those are like the first ones you should think of, but specific to your application, they're going to be different edge cases. So in this particular example, 100 is an edge case. That's going to be one of our edge cases that we want to make sure we hit, because there's a specific bug that can occur at 100 where we have a ones digit of 0 that should be a plus instead of a minus. We need to make sure we expose and eradicate that bug. So our test case job is to identify the bug, expose the bug, and then we can go into our code and fix that bug. So you're writing test cases for any bug that you can think of that might appear, running your tests. If the test fails, you go back to your code, you fix your code, you make sure you take care of that case, run your test again, hopefully it passes. This one will pass those 4 test cases, and then go back to writing more test cases. And then, as I mentioned, I would write a test case for like 101, 110, in case I give bonus points. All the different Fs, I want to make sure if you get a super bad grade, you don't like wrap back around to an A, things like that. And checking the boundaries, as I mentioned. So write tests to expose bugs. If you expose bugs, fix those bugs. That's your debug cycle. Yeah?
Quick question. If you're using hash maps, you should also use assert equals if you're comparing hash maps.
Not always, but yes. You shouldn't use equal for sure. So the question, if you're comparing 2 hash maps, if you should use equals or assert equals, you shouldn't use equal. That's for sure. If you use assert equals or the equals method, it's going to make sure you have all identical keys and all those keys mapped to identical values. So if that's what your expected behavior is, then you'd use equals or assert equals, yes. But we will have cases where we do actually have to manually go through the keys and values of hash maps and array lists. For example, I'll just spoil it, where I'm going to have an example, not an example, but a homework task where you'll have to compare 2 array lists of strings and make sure those strings are equal and in the same order within capitalization. So if one of them's all capitals and one's all lowercase, that's still good. But equals isn't going to work there because equals is just going to check if the 2 strings equal each other, which they don't. But for our purposes for that task, they will. So you're expected to iterate through the array list and manually compare the values. So we won't always get away with it, but definitely don't use equal. Yes, so the parameters for assert equals hint is expected then actual. I forget that all the time. The only reason I know it so good right now is because I messed up so much in the last lecture and my slides are messed up. So now I'm hyper aware that it's expected then actual. By tomorrow, I'll forget again. I don't know why. That never sticks in my brain. And the slide shouldn't be there. The website's updated. You can get the new slides. I just deleted it between lectures, but it takes a minute for it to update, and I wasn't delaying lecture for it. So we had this one failing too. This test failed. Why did this one fail? So this is a bit different than strings. Double is a primitive value, We don't have any references to objects on the heap shenanigans going on. So why does this one fail? And we saw the hint. I printed out why. We saw kind of why, but not really why. So let's talk about it. So if we multiply, and there's no magic here, by the way, I'm making a method call. I have a test suite. We got some stuff going on here. But if you just write a main method and print 0.1 times 3.0, that's where the error occurred. Just print those two values multiplied by each other. You're going to get 0.3 and then all these zeros and a 4. In fact, you'll get this in most programming languages. This is a fundamental thing of how computers work. You're not going to get exactly 0.3. And since it's not exactly 0.3, even though to us, that's basically 0.3, but to the computer, it's going to say, no, those are not equivalent values. They're not equivalent. This is going to result to false. They're not the same. Yeah. Why does it do that? Oh, I'm glad you asked. So, because of the way doubles are stored in the machine, so the short answer is truncation errors. We can't fit 0.3 in a double the way that the computer represents it. So a double is represented in 64 bits using this notation, this IEEE format. The sign, plus or minus 1 bit for the sign, 11 bits for an exponent, and 52 bits for the fraction portion. And this is represented using scientific notation, but in binary. So it's 1 point, the fraction part, raised to 2, or times 2 to the exponent. And then the sign, plus or minus, of course. So it's effectively scientific notation, but in binary. The problem is we can't represent every value in this format. It can't happen. So just a quick overview of how fractions work in binary. If I have the value 0.11 in binary, this is the same as the way we do this in decimal, where in decimal we have the tens place, the hundredths place, the thousandths place. In binary, it's the halves place, the quarters place, the eighths place, the sixteenths place. It's all powers of 2 instead of powers of 10, but it follows the same exact structure as decimal. So this is 1/2 plus 1/4. So 0.11 in binary is going to be 3/4. And in decimal, using this structure, there are certain numbers that we just can't represent. 1/3 is not equal to 0.3 no matter how many 3s we write, unless we write an infinite number of 3s, but we can't do that. Eventually, we're going to run out of paper, we're going to run out of space, we're going to run out of hard drive. We can't write infinite 3s, so 1/3 can't exactly be represented as a decimal, and 0.1, from our example, can't be exactly represented in a decimal in binary. It can in base 10, that's fine. 0.1, it's just 1/10. In binary, it would be this value, 0.0001100110011, repeating forever. Eventually, we have to just stop writing ones and zeros, which is going to be, once we fill up this fraction, after 52 bits, we stop writing ones and zeros, and we truncate the value. So we only get an approximation of 0.1 stored in the machine. Because we have finite space, we only have 64 bits, we don't have infinite space, so we stop writing them down, and we get an approximation. This is called a truncation error, because the truncation caused the value to not be exactly what we expect. It's extremely close, but it's not exact. And these truncation errors can cause our doubles to not be exactly what we expect them to be, because they're not. They're actually not exactly what we expect them to be. And that's why we'll get that 0.3 zeros and 4s. And you'll get that same value in multiple different languages because they're representing doubles in identical ways. So they'll get the exact same truncation errors. To a degree, we can predict these. But what we'll do in our testing is allow for some variance. We want to say, are these two values, or we don't want to say, are these two values equal? We want to say, are these two values close enough? Are these two doubles close enough to the same for our purposes? So we'll write a method that's going to compare the difference between the values and make sure the difference is less than some small value. So we're going to allow for some tolerance in our comparison, and then as long as they're equal within that tolerance, then we're going to say they're good. So in this case, 0.001, if they're within 0.001 of each other, I'm going to say they're good. and say, these are equal enough for my purposes, even though there could be some truncation errors. I don't care about those truncation errors. Just check if they're close enough. And there's a little bit of new syntax here, which I didn't have to use, but I used just because I feel like talking about it. It's 116. You're ready for some new things. Private, this is our first instance of private. That means this variable can only be used from within this class. So I'm saying nobody outside of this class is going to need this epsilon. I'm only going to use it inside this class. So don't even let them see it. I don't need them seeing this. Final, this is how we declare a constant in Java. Like const in JavaScript, same thing. The value can never change of this variable. Double is the type. Epsilon, I stole this from math. Whenever you have a value that's expected to be very small, they usually call it epsilon, so I just stole that. But I named it in all capital letters. Whenever you have a const in Java, this is standard convention that we name it with all capitals. If there are multiple words, we use underscores to separate them. And then I chose some value. This can differ depending on your application, what you choose for your epsilon values. I usually stick with 0.001 unless it makes sense to change it. But depending on your application, like if you're checking the distances between stars, maybe 0.001 is a little too small. You don't need to be quite that precise. If you're checking the distance between atoms, this should be way smaller. So depending on what your application is, you can think about what this should be. But in general, you want it small enough that it's not going to interfere with the logic of your test, but large enough that it's going to eliminate any truncation errors getting in your way. And then don't forget to do your absolute value. Take the absolute value of the difference. I see it every semester at least once. I'll see a student without the absolute value and just D1 minus D2 less than epsilon because they were just, working too fast and didn't copy everything from the slide. I don't know. But if I have 5.0 and a million, and I'm just taking the difference without absolute value, I'm going to have negative a bunch, which is less than 0.001. Test passes, even though you're off by about a million. Make sure you have that absolute value in there.